Well, thanks for, Amy, are you ready? You got it? Good. All right. I have a camera person here tonight. I'm so lucky. So thanks for coming. My name's Hank Roark. All my personal details that you can hunt me down with. I work at H2O. I primarily work H2O's this open source machine learning platform. There's a company behind it that provides support and most of the development, so I'm paid by them, but I'm going to try not to talk too much about commercial stuff today. Sometimes I slip into it because I do a lot of trying to get people to buy our services, but I'll do my best. So how many people here, I'm trying to get a poll of the group because I've got a presentation, but I can always filter it. So how many people here have used H2O as a package for machine learning stuff? Okay. How many people are here to learn a little bit more about H2O? Like they're hoping to, okay. Okay, that's most people. Okay, so, good deal. So yes, so I'm Hank Roark. I've been at H2O about a year. I go around and I help people figure out how to turn their business problems into data problems and then figure out how to solve them in machine learning. So I'm not a machine learning algorithms person. Actually, even with my degree in physics, I'm still lousy at math. I do a lot of applied work. Before joining H2O, I was with John Deere. Yes, that's the company that makes heavy equipment and lawnmowers. And some other things. I was always in kind of a weird part of Deere. We were flying airplanes and taking pictures of things and trying to do B2B commerce and lots of those machines in Deere have cellular telephones and cellular communication or satellite communication devices on them. There's a big database that captures a lot of data off of them, so I spent a lot of time trying to make sense out of that data and use it for feedback. So I'm not an engineer, I'm not a mechanical engineer, I'm not an electrical engineer. I can barely get all my electronics at home to work. But I have dealt a lot with geospatial and temporal data. And so I think that's why I'm here. So I've tried a few startups. I'm at another one called H2O. And you can kind of hunt me down. This presentation I'm getting ready to give, I've changed it, I've probably given it 3 times, so you're fourth. So I always get feedback and try to change it up a little bit. So everyone's an experiment for me. The problem is I have no repeated experiments. So one of the reasons that I got into the space was dealing with, and this is, on really big screens, it's not readable either. But this is if you're into data, I'm going to have a compelling example today of using H2O, kind of in this whole connected Internet of Things space, whatever the new acronym is this week of it. But one of the things is, this is a neat chart that shows all the different places where there's things that are getting connected to the Internet, that weren't connected before. There's a whole section down here that's called industrial, so that was where I was kind of working before. That's kind of GE's focus with what they're doing. But basically, I think if you're into data, this is an exciting place to be. The data sizes here get pretty big. So, like I said, that place I was prior, we ran one tiny experiment, and one tiny experiment, generated 30 terabytes of data. These days, it's not really big, but for the type of stuff we were doing, that was kind of big data. One experiment's 30 terabytes, so when you're running lots of experiments, it gets into decent data sizes. So if you're into data, I think the whole IoT space and how to make sense out of it is exciting and different. So one of them is I'm going to give this example of IoT data. I love this chart. It came from HP. But they're kind of talking about where will this IoT data go, and they're making this case that it'll go to brontobytes. So I just mentioned a 30 terabyte data set here at 10 to the 12th. So this is 15 orders of magnitude larger when we think about things that might be in the brontobyte size. I was wow, brontobytes. I love this slide because it lets me say brontobytes 5 or 6 times in a row. But they followed it up with how big is a brontobyte, and so we're now, the first time I gave this presentation is 2015, I think this chart was done in 2014. But you can see over here, there's a zettabyte, which says that'll be all the network traffic in 2016, so we'll see if the forecast actually came true. The yottabyte was, like I said, in 2014, it was kind of like the digital universe today, so it was like all the DVDs. The one that was the most disturbing. Oh yeah, it's here, right? A yottabyte is how much your government knows about you. It gives you some sense for scale. So anyway, so like if you're into data and you like doing data stuff, I think IoT is exciting. The other thing I think that's exciting about it, a lot of like because of my background and where I came from. I think that you've got this kind of whole loop that's going to happen, and it actually will probably cause you to think about how you deal with data differently. So it's one thing to get data, monitor it, but now we're talking about like sticking it into control systems. I mean, we're already doing that, right? I mean, being in the Midwest, we didn't have cars that drive themselves floating around, and here I try not to hit them. But yeah, so there's this whole loop of kind of re-instrumenting and re-controlling, and you need to kind of be able to do it fast. So anyway, I think IoT data is exciting, so I like to do examples with it. I'm lousy at doing like customer retention examples or credit risk examples, so I do IoT examples. So I have a very particular one for today. Actually, hold on. Wow, like I'm gonna really, I've given this talk enough times that open. As soon as I went to the next slide, I realized something really important, which is this is not the presentation. You would have gotten the same presentation somebody else had gotten. Open on my Mac. So one of the things I'll tell you, so everybody that's like taking pictures, I do appreciate you're welcome to continue doing it. I will say, like, I've also taken this presentation and I've stuck it up at, it's on H2O's GitHub, so I'll show you. There's a slide at the end that shows where it's at. So like all the presentations, all like the notebooks and everything, all the data to replicate this are all up on GitHub, so you can just grab it from there. So both in PowerPoint and PDF. So one of the things, so H2O is this machine learning open source platform. One of the hardest things about working at H2O as opposed to a company that generates data and has a lot of it is having access to data. You have to go out and you have to hunt down data. You have to hunt down public data because I can't talk about private data in like audiences like this. So you're kind of limited by what's out there. One of the hardest things about like machine learning data is that it's kind of data for the machine learning research community is it tends to not always be really big because somehow you got to be able to download this stuff, right, and be able to like distribute it. So it ends up not always being big data. So this was a decent sized data set. It was on prognostics and health management. It was for turbofan jet engines. So 40,000 pound thrust engines. These are the types of things that you would see hanging off of a wing of a commercial airliner, or you would see in gas turbine power generation facilities. They're all kind of in that size range. It was actually a challenge that was done by the Professional Society for Prognostics and Health Management. So that's the whole space of like figuring out if machines are going to fail and like their status in health. It was a challenge to say, can we use machine learning to help predict the remaining useful life? So like, how many times until this machine will cycle through until it stops operating? And the data that they published was challenging because they actually removed all of the context information from it. All you heard, you got just a few things, like here's a machine, it goes through a cycle, we take a sample of measurements from it, we take 23 sensor measurements off of it. We tell you what its operating mode is. We tell you that like we've built in manufacturing variability. We've built in, there's a random time that a failure is introduced into the machines. There's actually 2 different failure modes. There's actually 4 data sets. I'm using the most complicated one that has 2 failure modes and 6 different operating modes of manufacturing variability. And they give you 249 and they run them to failure, simulated run to failure. If you run one of these to failure, it's kind of expensive, it turns out. So like, they didn't actually do that. And there is a simulator that I still haven't been able to get from my government, but there's a simulator that will actually simulate this so you can generate more data. I haven't jumped through enough hoops. So they give you 249 to look at, and then you're to predict on 248 engines that you haven't seen before their failure. Like, how long do you have? Like, after the last observation, how many more cycles do you have until they fail? So that's kind of the challenge. So I always think motivating examples are good. So, so this will talk. This talks a little bit more toward like solving this problem, but I'll get into some H2O stuff here in a minute. So one of the ways, like I said, so you got these 23 sensor measurements. You get kind of a snapshot of every machine in time and cycles. And so one of the ways that you can do that is that you can do modeling on that data is by embedding the data into a phase space, right? So you can take a look at, because what you know is that the sensor measurements from prior states tell you something about the current state. So you're trying to incorporate this data that way. So there's a, wow, this looks really bad on this chart, but you can incorporate it into a phase space. You can take the sensor measures, you can do something like sensor measure number 1 at cycle number 1, sensor measurement, or at cycle number 7, for example. Then you can do sensor measurement number 1 at cycle number 6 and number 5. You can embed all of that out into a phase space. Okay. There's some head nodding, so I'm at least like getting it through eventually. Yeah.
Could you briefly say what phase space is?
Yeah. So in this case, so there's a couple ways that I've done embedding data into phase space. One of them is like this example, which is it's actually an EEG example. And they're embedding it through a time delay. So actually what you do is you say, instead of, I get a snapshot of the sensor at time t, I'm going to embed it into a higher dimensional space or add more features in machine learning language. So I'm going to embed it in t minus tau, t minus 2 tau. Other ways to do phase spaces, and you'll see these in some diagrams, is things like taking derivatives. So you'll take like the position, the velocity, and acceleration as a way to embed in like a higher dimensional phase space and just doing position at time t.
Then you just add those as columns.
And you just add them as features as columns. So that's one way to do that. So, and it worked, like sometimes it works. This time I decided not to do that. And there are some drawbacks to doing it. So one of them is that you only get yeah. Oh good, these are questions. I never get questions during these talks, I'm so excited.
In the phase space diagram you're showing over there, does one point correspond to data from a specific cycle, or are multiple cycles incorporated into one data point?
Yeah, so this isn't the phase space off of these jet engines. This is a phase space that I've referenced down here in the corner that's actually off of somewhere buried in an article because it was a pretty picture. So it's EEG data. So each one of these points represents information about time n minus tau, and or n plus tau in their case, n plus 2 tau. So
one data point.
One data point, yeah. So like I said, there's a couple of drawbacks. One of them is like it adds more features, right? So every time that you incorporate one of these, you have to add more features. So you have to kind of the curse of dimensionality problem that you see in machine learning. And then it's only a small number of prior states. So you only, unless you just go for infinity, but you have to like pick something, pick some number, do cross-validation, test it, see how well it does in prediction. And so like I kind of thought like there's got to be a better way to do this. And the way that to do that, to incorporate prior information, wow, okay. This looks a lot better on my computer, so I'll try to do this, is to use Kalman filters. Say, anybody who's familiar with Kalman filters? Okay, wow, okay. For all of you, I'm gonna seem like a dummy for everybody to raise their hand, so for everybody else, I'll do my best. How many people are familiar with like hidden Markov models? Okay, so Kalman filters are hidden Markov models, except with continuous variables instead of discrete. So everybody that knows hidden Markov models, I just described Kalman filters. So that's the first thing. But the whole point is that you have some belief about the state of the system, and it's probabilistic. You make a prediction based on the dynamics of the system about where it is in the future. You record observations, which is what this yellow thing is over here. You combine the two to come up with what the new state is. And then you use that and repeat it over and over again. And the neat thing about Kalman filters is they take into account all of the prior steps. They also, in this case, allow you to take into account something really useful about the machines, which is every time you go through a cycle, the remaining useful life decreases by 1. So it's the dynamics of the system. So you can incorporate that into the Kalman filter in terms of making this prediction. So how do you combine these two things together? And so this was my method for combining them together. So one, there's some feature engineering that goes on in this, and I'll show you what it took to do that. I called it quote-unquote signal processing because things are in a time domain that come off of sensors or signals, right? But it's just creating features. These were kind of trivial. Building through a regression modeling technique using supervised machine learning. You can pick your favorite. Pick a nonlinear one because these are nonlinear transforms from some high-dimensional sensor space to a single observation. So you treat this kind of machine learning as a nonlinear transform from the sensor space to the remaining useful life space, because you have that as a predictive column. So because you have 250, go to 0. And the neat thing is that you can actually build an ensemble on it. So you can use multiple machine learning models. So you can pick up random forest and GBM and deep learning and whatever else you want to pick up and ensemble them all together as measurements. And then use this knowledge about them being a linear dynamic system, right? It's a linear system, it decreases in step 1, and combine those and ensemble them through a Kalman filter. So I'll show you how I did that with H2O. Any questions? Okay, cool. So the first thing is this is what the data looks like. This is a sample of 3 machines for a couple of the sensor measurements, and this is time along the y-axis here, or the x-axis horizontally. 0 remaining life is here, and what's interesting about this data is there's not really any observable trends over time, so it becomes really quite hard to figure out how to actually do stuff with them.
What's on the y-axis?
The y-axis is just the sensor measurement, and they filtered out all of the information. They just go here's a sensor measurement. We're not telling you anything about what sensor this is, because they want to hide all the physics from they purposely tried to hide all the physics from people trying to solve this challenge. Ask the question again so that I could. It's not catastrophic. It's actually when it stops. It's not a catastrophic failure. It's when it fails to achieve its requirements. So the machine goes below some requirements threshold for performance. Yeah, that's how they defined it. And then they didn't tell you what that was. So, yeah. So it could have been just time for maintenance, right? Like you start at 1 and it didn't start, or whatever it is. You couldn't achieve your requirements. Was the only definition they gave you. Which is, a lot of times, when I do data science stuff, I like to get context because it lets me put a lot of information into it. They gave almost no context, so it makes it both interesting and challenging.
What is Boolean indexing?
So this is, since if you'll bear with me, what I want to do is that since I got people asking about H2O, I'd actually taken out a bunch of stuff around the H2O pieces of this. So let me bear with me and let me show bits and pieces of using H2O, and then that will make more sense because it makes no sense in this context. Back to what H2O is. So H2O is this platform for doing machine learning on. So this is a peek piece of this. The way you kind of deal with H2O is that you load data into H2O. It's not an online learner, it's all stateful. So when you do this inside of H2O, so I'm going to talk a little bit about H2O for a while, not the domain problem, is H2O is a service that runs, so it doesn't run in Python or R, it runs in actually a JVM process space, but you can access it from R and Python. So when you make this remote call to H2O to load data into it, if you're running in a single machine, and in this case a cluster of machines, you're actually making a call out to the H2O service to load data. So these are for the people that want to learn more about H2O and how it works. that if you're running it in a cluster environment, it tells H2O to load data from disk. So if it's in, or on a single machine, it'll tell it to load it from disk, and it just returns a pointer back to the H2O. So that's like, H2O has a structure that looks like a data frame. This is a long way to answer the question about the Boolean indexing. But it looks like a data frame like you're used to in R or Pandas, mostly. It's kind of how the API holds it. So when you need to go and do things like you want to look at this data, so there's a couple of things I had to do with this data. The first thing is creating the target variable. So I'm just going to kind of walk through some code. I'm actually not going to walk through code because that's the most boring talk like in the world. I'm just going to point at some code and then tell you all where it's at. But I think the point that I'm trying to make here is that like H2O gives you some capability to do what I consider fairly typical data prep steps that need to happen. So the first one is there's no target variable that comes with the data, you just have to create it. It's not very hard to create, but it's a pretty normal sort of step where you go and you calculate some metric, in this case, what's the maximum number of cycles for each machine, that's by unit number. Merge that summary statistic back into the original data frame, do some other calculation on it, so this is what gets you a decreasing number of remaining useful life, and actually drop the, and then also drop that temporary column you have. So H2O has these capabilities through a Python API to allow you to do feature engineering like this, and it looks a lot like what you might get with Pandas. Not exactly, but a lot like it. And so this is probably this is an example of using it. So the other piece that you can do is like, there's all kinds of other things you can do with H2O. So I wanted to pull a sample of the data from H2O, which is running in this Java space, pull the data actually back into the Python space so I could use Seaborn for plotting. And one of the reasons this talk is, since there weren't very people that tried H2O, H2O's went through like 2 or 3 major revisions of its Python API, so this is the newest one, and I think we're kind of like it's sticking with the community, so it's going to stay around like this. The prior version before it looked, the code that you would write would look like our code in Python, which the Python community said like we're very confused, like we're using these tools like Pandas and scikit-learn, like make it look like Pandas and scikit-learn, like why can't you make the API kind of familiar? So this is, how you would go, this is how to get a sample of the data, and in this case it's just pulling out, setting a set of booleans, and so I'm just trying to get units 1 and 2 into another data frame, from this data frame into this data frame, and then that gives me a sample of the data I can pull into the Python space and then integrate it in for plotting and stuff. So that's where the Boolean indexing stuff came from. So the next step is actually sample the data to local memory. So I created a sample of the data in H2O and JVM, just data really big, it'd be in a big cluster distributed. And then this would actually pull it across the wire through a REST call into wherever I'm running Python at, and allow me to go and then use all my Python tools on it, which I did. So yes, use some, there's no trends over time. So there's sensors. We'd like for these sensors to show us some trends over time. They don't, they're kind of noisy, so what's going on? And so the answer is that, wow, this is even an older deck than the last one. It turns out that if you look at one of these sensor measures, they actually come in 6 groups. It's 1, 2, 3, 4, 5, 6 groups. And so simple clustering will allow you to do feature engineering and figure out which one of these operating states. So we already knew there were 6 operating states. Yep?
What does it mean by 6 groups? What's X, Y axis?
Yeah, so X, Y axis here is, this is a sensor, these are, let's see. Yes, so this is one sensor measurement, good question. This is one sensor measurement by the operational state it's in. So it's just a way to visualize that there were actually 6 operational states, and the sensor measurements that you get, the reason they're random is because the machines are going through these different operating states on each measurement. So you can see here there's 6 groups. If you look at it from a different perspective, which is all this is rotation about some axis, it shows 5 groups, but it turns out it's 6 groups. So the whole point is that if you know which one of its groups is in, you might be able to do something to get these trends over time. It's the hypothesis. So in H2O, in the new API, it's this estimator API, so you'll find one. This is for k-means for clustering, and it looks a lot like scikit. Matter of fact, those are scikit estimators. You can put them into scikit pipelines. But it's all running kind of remotely inside of H2O. So it's how you set it up. I know the number of operating modes. I don't have to go through and figure out the number of clusters. And then I can generate and then use that as a way to create and append the operating modes to the original data, which gives me a new feature. With those, you can do some really neat feature engineering inside of H2O. This is like nasty Python code, but it works. So I called it done because I didn't have any more time to spend on the problem. But it basically then standardizes, it throws out all the sensor measurements that are constant within a single operating mode because they don't tell you anything. And then it standardizes each sensor measurement by which one of those 6 operating modes it was in, all on the training data, applies it to training and test data separately. What ends up happening is that you go from data that looks like this. This is a single sensor measurement, this is time, this is the measurement of that sensor, from stuff like this to things that look like this, which actually shows some trends of the sensor measurements over time. The best I can tell is that these ones that, like on this measurement, I forget which number it is, it's number sensor, it's even small on my screen, 7, sensor measurement 7. It goes up for one of the failure modes and it kind of trends downward for another one of the failure modes. So it allows us to then use it inside of a learning algorithm. So that's the way that went. I want to switch back to the other slides. Let's go ahead and look at this. So yes, so what I do is I run through, I then use, I've actually had no luck getting a deep learning model to work on this data, largely because I'm not Arno Kendall, and I'm not a deep learning expert. So I ended up using gradient boosting estimators to make this work for H2O. What this is H2O's GBM. So you import the gradient boosting estimator. These are actually brand new features inside of like the latest version of H2O. So this is a Laplace law. So it's it actually uses absolute error instead of a Gaussian error. And it turns out like in cross-validation, this just worked better. So I picked it. There's no particular reason. These sets of measurements here with H2O are all about early stopping. So GBMs, right, if you train too many trees on them, they can overfit the data. And so H2O has some new functions in it to actually stop as you get to, as building more trees decreases to a certain rate. So that's, improvement decreases to a certain rate. So that's what that does inside of H2O. There's a couple other things that are kind of interesting. So H2O has, here's how you define the independent and dependent variables. So the target is this, setting up the remaining useful life. There's a cross-validation step. So it has both validation data, in-fold validation, and this one in your training frame, you can actually put a fold column in, and you can specify the folds external to H2O. So that's really useful for this because what I wanted to do was take each one of the 249 machines, take a fifth, take 4/5 of them, and use those to build a cross-validation model on the other fifth. So I'm actually able to use the unit number as my cross-validation piece. So that ended up being very, very useful. And then I actually wanted, one of the things when they do the scoring on this challenge is the closer it was to failure, there were some more errors. The way they scored you is that the closer you were to failure, the more precise you had to be, basically. So I was able to, H2O has, and built inside of everything, also has weight, so I was able to weight the ones that are later in the life cycle to use a weight column, so all kind of built into H2O. This model, does anybody dare me to do like live, like does it really work? Yeah, okay. There we go. It's gonna work. It takes a while, this model takes a while to run on my tiny little laptop. Like 5 or 6 minutes, so we'll let it go. It does 5-fold cross-validation. It builds an end model. It ends up building 166 trees on average. They show you can, like, not only does it, when you're doing this sort of, whenever you provide some sort of validation stuff, it both does model building and scoring at the same time, both on training and validation data, so you get all those metrics out. Nothing like live demos. And then in this case, where I was getting at is that the Kalman filter, which is actually from, so this is a step of getting the data ready for the Kalman filter, but when I'm doing this 5-fold cross-validation, I get 1 overall GBM model, and then I get 5 cross-validated models, so I get 6 models in total. So with the exception of, like, I just ran out of time for cross-validation, this picks up all 6 of the models, uses H2O for prediction on the unseen test data, and then binds them together in a way that's friendly for PyKalman. So there's this package called PyKalman. Has anybody used it for Kalman filters? Okay, so one of the great things about, like, doing stuff in kind of the open source space is I don't have to go out and get commercial stuff. So I set up the Kalman input. So there's a couple things that I use to do it. So one of them is that each one of the models, 6 models in this case, is treated as a sensor measurement, right? It's a measurement of remaining useful life. So you have, like, 6 measurements in each space. But the state that I'm using in the Kalman filter is actually just a simple 2-entry vector. It's both how many cycles do you predict are remaining, and what is the rate of decay of cycles between state to state. You initialize it with the mean of the remaining useful life from step 1 of each one of the 6 measurements. So you use the 6 as a way to do a mean. It's the best thing I could come up with. And you use the MSE from each one of the 6 models to give you the covariance matrix, because you need in Kalman filters to talk about how the sensors covary between each other. And then this is, and you initialize the state decay to -1 per step. So it says, like, I expect that this thing should, like, be remaining useful life. Every cycle should go down by 1. So you can do that, and what you end up with is, this is a plot. This is time on this axis. This is cycle numbers. This is predicted remaining useful life. This is for one machine number 2 that I picked because I didn't want to pick machine number 1. And you can see here, this is the nonlinear transform. This is just what one of them predicts as the remaining useful life. And you can see it kind of fluctuates a lot over each one of these steps. And what the Kalman filters do is they basically act as a way to smooth that data out and use the prior steps for calculating what comes out of it. So this is the exact same machine except passed through that Kalman filter with 6 of them ensemble. But you still see things like this, right? You see these big gaps and those types of things. So maybe there should be some more smoothing on it. And then from there, you can do a plot. This plot, I've got everybody asking me about Axis. This is for each one of the 248 machines. This is the actual remaining useful life, so they actually provide you a file and tell you what it is now that the challenge is over. And then they give you the predicted, this is my prediction on it using the Kalman filters. There's a score up here. I'll tell you that score, like, I no longer, the first time I gave this talk, I had a lot of confidence in that score because I was being, like, a really good data scientist and only, like, calculating it once. But I think I've cheated enough times that score keeps coming down on me. I'm afraid I'm letting the test data leak back into my modeling because I do new modeling work. So it keeps coming down, but when I did it the first time, it would have still been like a top 10 in the competition. So it worked out okay. The thing is that you want it as close to the dash line as possible. It's closer to the dash line, the closer it is to 0. There's still some, like, lots of opportunities for improvement because it's still biased this direction above the line, which is actually bad because it says, like, oh, my predicted remaining useful life was 35 cycles, but I've only got, like, 10 left. So there's some bias in this that could work out. So yeah, so that's kind of like the whole sort of presentation, unless I find the other slide. So what I'd say is like, there's just lots of opportunities to combine these things together. You can use it in the input space. A lot of signal processing happens before you actually do the machine learning pieces if you're trying to do prediction. You're either doing filtering or some sort of convolution. You're doing dynamic time warping. You're trying to get things on the same time axis. I've recently started experimenting with recurrent neural networks, which seem to learn a lot of these features that I'm having to like use my domain knowledge to program in. So that's another place to go do stuff like that. And what I'd say is like, I'll find the slide that actually has where all this stuff is posted. For anybody that's interested in H2O, like I'll answer questions about that, or I can answer questions about this problem. We did bring these little yellow booklets that talk about the Python API. So this is a printed version, but there's actually electronic versions of it for Python, R, GBM, deep learning, and generalized linear models, like little booklets that are kind of very technical vignettes. So it's a way to get more information. And then the meetup GitHub for H2O will have this slide deck and everything in it. So I'll take questions now. Great. More questions. Awesome. We'll start here.
So it seems like one of the big tricks when using this method is trying to find the right kind of Kalman state predictor that has a pretty straightforward going from year to year and a half to year.
Yeah. Yeah, so you're taking
What was the question?
oh, yeah, so we'll do this.
The question was that it seems like one of the big tricks with using this method is finding the right kind of Kalman state predictor, the right kind of formula to go from state A to state B that has a nice smooth transition.
Yeah, so great question. So yeah, so absolutely, like I had to put in, like some information about the initial state, like that my expectation is that the state decays by state 1, and then I had to put in a transition matrix that took into account this state transition. So yeah, you got to get the transition matrices and all of that right. So yeah, there is a lot of work with trying to figure out those and get them into and get them programmed. Matter of fact, it's been a while since I gave this talk, so I had to go back and look up what all of them are that I put in here. So yeah, so that's like, you have to know it's a linear dynamic system, or you have to make the assumption it's a linear dynamic system and then figure out how you're going to take advantage of that. So yeah, absolutely. It's domain knowledge, right? So, yep. Yes. Yes, great. Thank you for saving me from talking for.
Did you perform any tuning on the model, and if so, how?
Oh. Yeah, so there's a much longer version of this that actually has, it has a whole pipeline for tuning. So post the feature engineering, which I feel is kind of good. But it did grid searches on GBM, it looked at multiple models, and then it included both the filtering and non-filtering to see if it would work. And also, like, should I include all of these cross-validation models? Which ones should I include? So there's an older version, probably back in October, that had a lot more kind of full pipeline cross-validation. But you gotta, like, the thing is, it's like any other sort of machine learning stack, you gotta wrap everything that you're doing in like a big cross-validation loop. Yeah. Did that answer your question? Yeah. Okay, great, awesome. I'm gonna run this mic back because it lets me drink some water.
You talk about the Kalman filters and the predictions you have in each model, but how do you test your software? For example, if your prediction is out of your let me redo it. You talk about the Kalman filter. I already know it, and all the filters you can get to put a prediction on your model. But how do you, for example, I made a software to test something, and how do I know that my software was going well? For example, how do I test my software, not the result of it?
Oh, how do you like actually?
Yes, in the IoT model.
Oh yeah. So how do you? Yeah. So let me see if I can answer it. Let me see if I can even like restate the question, right? So like, there's like, how do you test the software, right? Like not the
pre-test is before the test the model. For example, I develop the software,
and have the curve and all. I don't know if it's a deep question or.
Yeah, I think it's, so I think that's actually a really hard question, right? A really hard question to answer. And if anybody knows the magic, H2O's hiring. So I'll like leave it there, right? Because one of the challenges with like doing anything that's got this data intensive piece to it is it's an interaction of the data and the software, and sometimes the environment that you're in too, right?
It's cross data all the time.
Yeah, so you gotta make sure all the bits and pieces work. It's like, it's one of the reasons like we don't spend any time doing benchmarking of H2O because like, one, you can lie in benchmarks. Like we all know we can lie in benchmarks, right? It's a type of test, so we'll use benchmarks as a type of test. But the other one is that the data interaction matters more, it matters a tremendous amount about the performance. And so like as a test, right, like we'll call it a performance test, like the data interaction makes it hard. So like I'll tell you what our approach is, at least in terms of machine learning algorithms, which is we just try to collect as many data sets as we can and compare it to like a gold standard, right? Sometimes the gold standard is there's actual real analytical, absolute, exact solutions, right? So you're testing an optimizer, some sort of stochastic optimizer or something against an analytic solution. And when there's not, we set error bars and say like, hey, like does the thing produce the data that we'd expect to have with these error bars? And I'll tell you, like it's hard. Like it's hard.
I was thinking about the pre-testing.
Yeah, absolutely. Great question. Great question. You got a question? Oh, well, ask it. Yeah, like micro questions are great.
On your notebook it said Python 2 up there?
Yes. Oh, yes. So, as of 2 weeks ago, H2O now supports Python 3. So yeah, you can move it forward. I'm going to get electrocuted. You can move it forward to Python 3. So I just haven't done that yet. And the reason was I hadn't checked yet if Kalman like works in Python 3, so I just left it there. So that's new things that came out in H2O this week included Python 3 support. There's now this both quantile and Laplace distributions in GVM and deep learning. There's some new randomized grid search capabilities that do, instead of just, if you're doing cross-validation models or grid search models for the right hyperparameters, there's a new randomized search in the hyperparameter space that came out recently. There's also, what else is in H2O open source new? There's ordinary least squares, so there's actually like, you can do non-regularized generalized linear models, so regular generalized linear models, and actually get out things like standard errors and p-values and those types of things. So there's just some new things in it, and Python 3 support. Woohoo, Python 3, about time. Next question, did I see a question back here? Yeah, okay.
He's going to have a smarter question, but the Boolean indexing that was asked earlier, to reiterate the answer, it's simply, is it above or below this filter?
Oh yeah, this was just, so the Boolean indexing I was doing was just to pull a sample of the data into a data frame, so I wanted to pull out, so it's just a way, you know how Pandas has Boolean indexing for like selecting into a Pandas data frame? H2O has the same sort of thing, and so the reason it's up there is to show like, these things that you should expect to work in Pandas work inside of H2O on much bigger data sets.
And when you're moving, because you said you moved the data out of the database, and then it was like in an application layer or something. So in general, are you removing it from database? How does it connect to Spark or something?
Oh yeah. So let me ask some more H2O questions. So H2O 3 is this Java library for doing machine learning, and the kind of magic of it is that it works, like all the algorithms in it are parallel and they can be distributed across multiple machines. So like if you run it and you run GVM and you run it on your laptop, right, and you've been running GVM, whatever Sidekick comes with or whatever R comes with, and you get like one CPU out of 8, like even on your desktop machine working, H2O will use all 8 of them and do stuff. If you have multiple machines, or data that doesn't fit on memory of a single machine, you can work that way. So what H2O as a library can do is it's been taken and put in an environment so it can run in a desktop. We can start it from the command line and run it as a, a desktop app. It's got like a web route or web user interface called Flow. Install models. So these are the models I ran today. So this is one way to get H2O to its UI. It's also been it's also got this like Python API, and you can initialize the JVM from inside of Python or outside of Python and connect to wherever you're running H2O. And for Spark, so what H2O natively can read is really, it can read off a disk. It doesn't really read off a database. It reads like CSV files, some sort of delimited file, ORC, SVM-Lite, Excel files. I think Parquet is getting added. Some normal like Hadoop files, right? And then, but inside of Spark, there's a version of H2O, so that library that's been used and put all kinds of places. It's been on a desktop, you can launch it from Python, you can launch it from R. It's been taken, and you can go to AI, downloads. So over here is kind of like H2O that's not for Spark. So there's this desktop version, R version. There's this H2O for Hadoop. So took that Java library and wrapped it in some things so it runs as a map job and as a long-running map job, and you can deploy it into it's wrapped for Cloudera, Hortonworks, MapR, and you can basically initialize H2O as a Hadoop jar command inside of Hadoop. Inside of Spark, the way H2O works is, which I have not done the Spark version of this, is that same library for H2O is taken and it's wrapped to make it easy to get data in and out of RD data frames and soon to be data sets, and into H2O's internal memory representation, which is called an H2O frame. And it's called Sparkling Water. So that's the interaction of H2O with Spark. So there's a version called Sparkling Water, Spark 1.4 and 1.5, 1.3. You'll be like, we've kind of dropped 1.3 recently. We can still get you a version that works with 1.3 if you need it. If you use it inside of Spark, there's two APIs to get an H2O with. There's the Scala API, which is really a Sparkling Water, which is a very thin wrapper of kind of API, and then the Java APIs that H2O publishes and makes available. And there's lots of examples for it in like the GitHub repository to actually be downloaded. If you use H2O inside of Spark with Python, there's a little bit of extra API for Python, like you have to set up an H2O context and some things. But actually, everything else around the Python API is 100% the same between like regular H2O and H2O inside of Spark. So that's how, and so the way to think about H2O inside of Spark is it sits right there, like next to MLlib. It's another library for doing machine learning with. And then it interacts with the rest of the Spark ecosystem as a library. Did that answer? Okay, great. Cool.
Does it interact well with the streaming operators of Spark?
Oh, yeah. So there's a couple ways to use, and we have some examples of it, maybe in the download, and if not in the Sparkling Water GitHub. There's lots of examples there. There's two ways to use H2O inside the streaming environment. So one of them is that you start up H2O and you can actually run predictions. We've got examples of you running, building a model and then using streaming and running it through H2O's predict model. Actually, it runs through a couple. There's one that's called the Craigslist example, so it uses some of the NLP stuff in MLlib to actually do work with that. And then it uses that for building a model inside of, they told me not to hold the bottom. It uses that for then as input into like a GVM model for making predictions. And so there's an example, and then it uses the streaming setup, so they can type in new titles for like job postings. It'll tell you which one of 6 categories it might go into. So there's, like, that's one way of using streaming. The other way is that when H2O builds a model, you can export all of the machine learning models as Java objects. You can take the Java object, you'll put it anywhere you've got a JVM. So you can just compile it, and there's some examples of compiling it and loading it back up as a step inside of a Spark stream. Yeah. Or wherever you need to do streaming, like it's, because it's just a Java object. It doesn't require this whole like model building infrastructure. It's kind of a standalone Java object that hard codes all the parameters. Yeah. Yeah, there is an option to train a model in online way and then use it, yeah. Yeah, there's lots of, like, I'm always surprised by what we can do with it, so.
Good. So you made passing reference to a recurrent neural network, and it seems like the Kalman filter is well suited to physics-related kinds of objects, whereas ones that are more non-stationary in their characteristics might be better suited to an RNN kind of an approach. And I just wondered if you could elaborate on that. Is that in Arno's area, or do you incorporate it here, or how do you go about providing for issues such as with a Kalman filter, you have to adjust the gain, let's say, so it forgets things rather than always learning, and that becomes complicated. So how do you deal with data that is transitory?
So there was a lot wrapped up in that question. So let me kind of walk through like the bits and pieces, and I'm not going to answer a lot of it as the answer. So the first question was around like you know, that just kind of the application RNN. So one, like I'm getting new into that space, so like I'm not going to say much about it other than like I keep experimenting, and I'm kind of like encouraged is the answer, right? So that's kind of exciting. Another question might be is like, what's H2O's plans around, you know, some other neural networks? And so we're experimenting, like Arno, which is the chief architect and kind of deep learning guru, he's experimenting with how we can incorporate it, because the current deep learning stuff inside of H2O is a fully connected feed-forward neural network, just plain old neural network with things that you'd expect to have in one, you know, but no convolutional layers, no recurrent, no LSTM. So he's experimenting with how we can incorporate that. And actually take advantage of GPUs, because H2O is like a pure CPU play right now. So, one, that's another one is like stay posted with that. The in terms of non-stationary learning, I think that's a really I think that's a really exciting place. Like, and one that like I don't feel like I know enough about right now. I will say, like, I was working with a company that had a non-stationary problem, and we run into them all the time, because like, so these are physics ones. The non-stationary problem in this case was actually transaction fraud. Fraudsters figure out how to do stuff really well. So one of the ways is to build very robust models, and certainly people are doing that. You'd be amazed by how long the models that protect your credit cards from like credit card transaction fraud, how infrequently they get updated. I was shocked by how infrequently they get updated. At least the machine, you know, kind of the statistical models behind them. The challenge with them is, and this is, I can't claim the statement, it was actually somebody much brighter than me. So like that was one of their challenges with like actually using machine learning models in that environment was they're not robust to kind of these non-stationary changes, whereas they were building more robust statistics-based models. But they were starting to experiment more with machine learning models if they could turn the deployment cycle over quicker. The deployment to production, right? So, because like if you go to an engineer and say like, I've got a GVM, like could you code it in some Java code? Like it's hard, right? So like we're still experimenting with like they're looking at like this like how fast can you move? So this is where like H2O's Java objects or PMML allow you to get to production faster. So I don't know that I completely answered your question because I don't have a really great answer for it. But yeah, so yeah, I was, gosh, where was I? Oh, I was in New York with a group, and they were like, they had to build models that were robust to macroeconomic factors, kind of a common non-stationary problem, right? And we got to talking. I used the exact same math, except I was trying to build models that were robust to weather, because weather matters in agriculture at the time. So, like, I don't know, like, I think there's a lot of opportunities to like do learning in that space. I've got a book on my desk I haven't had a chance to read yet on non-stationary models. So it's a good question.